Hello students, last time we have discussed about the physical concept of electromagnetically induced transparency. Today I am going to discuss about electromagnetically induced transparency, but mathematically we should know about mathematically how we can derive the susceptibility of the atomic medium and how we can get the EIT window. So the first thing is we should consider an atomic medium. So last time we consider uh, atomic medium, and now we pick one atom, and this atom consists of three levels: A, B, and C. And here a probe field is applied between A and B, which has detuning delta P, and the strong field is applied between A and C, which has Rabi frequency omega 1, and this is Rabi frequency omega p, and the decay from level A to level B is denoted by gamma 1, and the decay from level A to level C is denoted by gamma 2, and there is a collisional decay. There is no coherence between B and C, but due to some collision, we can take gamma, the capital gamma. This decay is very small, but one can consider that this decay can play some role. The first thing of this uh, configuration, we need to write down the Hamiltonian for this system. So the interaction picture Hamiltonian for this system is this H, which is equal to minus H cut divided by 2 omega P. This has been applied between A and B. So omega P, which has some detuning e to the power minus iota delta Pt. So this is applied between A and B, so we can take these states. The omega 1 is applied between A and C, then we can write omega 1 AC, but there is a no exponential e to the power minus iota delta t, because here there is no detuning between A. So the detuning here, the this field is completely resonant with this transition frequency. So the detuning is equal to 0. So if the detuning becomes equal to 0, then exponential power 0 is equal to 1. So we have only omega 1 AC. Now, the conjugate, we should consider the conjugate of this and this. So this is the conjugate of this, and this is the conjugate of this. So this is the Hamiltonian for a system. Now to find the density matrix equation, so we use the density matrix approach, and we use this relation rho dot, which is equal to minus iota divided by h cut, h rho, this is the commutation, and this is the anti-commutator, gamma rho. So this part shows the decay of the system. So this equation is denoted by 1. Now, to find the optical susceptibility of the medium, we need to find out the coherence between these. We need to find out rho AB first, because this is the coherence that we need to find this first. So rho dot AB. We need this one. And how to find this? We should take the A from this side and B from this side to this whole equation, and we can get row AB such like this, row dot AB. Then it means that we can write down A row dot B. So this is actually row dot AB. And here we can also apply A from this side, B from this side. So A from this side, B, A, and B. This is equation number 2. And for simplicity, I can take uh, this one, A, H row, and B, and the second one, A, row H, B, and separately I can find out. For example, I can take A, H row B. So this part, and put the Hamiltonian. This Hamiltonian we should put here, and then after some operation, we can get this equation, minus h cut divided by 2 omega p this and this. And to find A row HB, so this I have find out, put the value of H and operate from this side and this side, we can get minus h cut divided by 2 and this. Remember that this A and B, this will be equal to 0, and A, this will be equal to 1, and B, this will also equal to 1. So this is orthogonality condition, so you should know about this. Now I find out this, and also we can find out this decay part as well. So there are also two parts. We can consider A gamma rho B and A rho gamma B. Then if I consider this A, this, if I apply this separately, then A gamma rho B, A rho gamma B, and gamma is journal decay. So I have considered this is a journal one. So gamma rho AB plus gamma rho AB, and this is, if we add this, this will come 2 gamma rho AB. Now put this, and this in equation number 2. Then we have this kind of equation. And finally, we have rho dot AB, which is equal to iota divided by 2 omega p e to the power minus iota delta pt, rho BB minus rho AA plus this CB minus gamma 1 AB. So actually this gamma is generalized decay. I have considered this as a generalized one. You can consider by your this is your choice what this decay is, because this is a generalized equation. If this is gamma 1, then this will be, this capital gamma will be gamma 1. If this is gamma 2, then you can consider this gamma 2, and so on, whatever you want, and how you consider the decay. So this depends upon you. Similarly, we have to find out rho dot CB, because in this equation, if you look this one, this equation has rho BB, rho AA, and rho CB. So this rho CB we should need, uh, and rho BB and rho AA we also need for these equation. But if we apply the perturbation theory next, then these two equation rho BB, rho AA will go to 0 and 1. So we don't need to find out the other equation. But for your practice, you can find out all these equations. So actually this rho dot AB, then rho dot BA, take the conjugate of this, and this is rho dot CB, take the conjugate of this equation, then this will rho dot BC will be equal to minus iota divided by 2. This is BA, this will become plus, this will be AC, and gamma CP, BC. So you can take the conjugate of these. So you can make four equations from this, and rho AA, rho BB, rho CC you can find out. So try yourself and find out these equations. Now are we have two equations, this and this. I will write down this separately. From these two equations, we should remove the time part, and how it is possible. So there is some approximation we have to consider. Approximation such as, consider rho dot AB, which is equal to rho AB tilde these two equation, rho dot is equal to this, and rho C dot, sorry, there is no dot, this is only rho AB which is equal to this, and rho CB which is equal to this, is only tilde. Differentiate this equation, rho dot AB, then with time, so these two are in products, so use the product rule, rho AB dot e to the power minus iota delta pt plus rho AB and minus iota delta p and e to the power minus iota delta pt. But AB, which is equal to rho AB e to the power minus iota delta pt minus iota delta p rho a b e to the power minus iota delta pt. So this equation I have considered this and then differentiate because I have to put here. So from this equation rho dot AB is equal to this. So put the value of this here. So from this equation, this is equal to rho A P e to the power minus iota delta pt minus iota delta p e to the power minus iota delta pt, and then iota divided by 2 omega p e to the power minus iota delta pt, and rho bb. This is as it is. We have we can consider rho bb, which is equal to rho bb, and rho aa, which is equal to rho bb. So consider this, rho bb minus rho aa plus iota divided by 2 omega 1, and rho cb, I have considered rho cb e to the power minus iota delta pt minus gamma 1, and rho ab. Rho ab I have considered this rho ab and e to the power minus iota delta pt. Now look this equation, and you can ignore the time exponential part. This with cancel. So the left hand side and the right hand side, the exponential part will vanish, and we can get only rho dot AB, and this minus should go this side, iota delta P, and here I think this is here there will be rho. mm, there must be rho, yes, there must be rho AB. So rho AB, and here iota divided by 2 omega p rho bb minus rho AA, and plus iota divided by 2 rho cb minus also omega 1 and minus gamma 1 rho AB. So this is the equation that I have derived, this one, and similarly, this is for your practice. Similarly, try and put rho say be this, first differentiate with time rho dot say be, and put here, here, and here, and you can get the equation. So finally, we have these two equations, and now the we have to use the perturbation theory to reduce these equations. Actually, there are other equations: rho bb, rho aa, rho ca. So, how to reduce these equations, add equations to 2? So we have to use a perturbation theory, and this perturbation theory is helpful to reduce the add coupled equation to only two coupled equations. Let's see. So EIT is a linear process. We have to consider this in first order. The probe field must be in first order, but the control field or pump field may be in second order and higher order, because the omega 1 we have considered is a strong field, so we can consider this in second order or higher order, because this is a strong field, and probe field is a weak field, so we have to consider this is in the first order. So how to do this? We have to use this kind of approach. Actually, we have to need this one. So if we consider this is in the first order, so here we have the first order as well. Here the probe field as in the first order. If we consider this is in the first, then this will go to higher order. So we must restrict this in the zeroth order. And here as well, we must have to consider this in the zeroth order, because this is omega p. So if we consider, for example, if we consider this in 1, then omega p and this, it goes to second order, and this as well. Now here, I have considered this in 1 because omega 1 is a strong field, so 1, 1, this will go to the higher order, so no problem. But we cannot take this and 2, because this is a linear process. We have considered this in 1, so this must be 1. So maybe this will be in the second order. Similarly, this rho CB is in first order, so this will be in first order. There is no control or probe field, so we can consider this in the first order. This is a control field, we can consider this in the first order. Here, once again, this is omega p, and this is rho Ca. If I consider this is around 1, this will go to the second order, so we must restrict this as well in the zeroth order. Now, what is the situation? The situation is row BB0 in the zeroth order, in the initial condition. Initial condition for this EIT system, initially the atoms are prepared in the ground state. All the electrons are prepared in the ground state here in B, and there is no electron in the A and C state. So initially, uh, this is the initial condition, rho BB0. This is the initial condition. So initial condition is this rho BB0, this goes to equal and 1, equal to 1. Now, the initial condition of the excited state. So initial condition is all the electrons are here, so there is no electron here, so this must goes to 0. And here, this is also equal to 0. But why? Why this is equal to 0? Because initially the atoms are prepared here and the probe field is applied from B to A. So this rho CA, this will not affect the coherence of AC. So initially we should consider this is equal to 0. Now the final two equations we have rho AB, which is equal to iota delta P minus gamma 1 rho AB. This is 1 1, this is for your understanding I have write down. So if I remove, so there is no problem. Plus iota divided by 2 omega P, this is 1, this is 0, plus iota divided by 2 omega 1 rho CB. And this equation rho CB dot, which is equal to iota delta P minus gamma rho CB plus iota divided by 2 omega 1 rho AB. Now these two equations, if you look to these two equations, rho AB, here rho AB and rho CB. And this rho CB is equal to rho CB and rho AB. So these two equations are coupled equations. And we have removed the all other six equations by using the perturbation theory here. So this is the technique that we have to use and reduce the equations. Now, our system, after some time, our system remains constant and there is no changing when the time is passing. So for that, we have to use the steady state situation. The steady state means the coherence is not changing with time. So the left hand side of these two equations must equal to 0. So the steady state equation will be now the steady state equations may be this is equal to 0, so this is equal to 0 and this is equal to 0. So write down this iota delta P minus gamma 1 rho AB plus iota divided by 2 omega P plus iota divided by 2 omega 1 rho CB, which is equal to 0, and this is also equal to 0. Delta P minus gamma rho CB plus iota divided by 2 omega 1 rho AB, which is equal to 0. So we have these two equations. Now we need, as we discussed already, we need for the coherence this one rho AB. We need for the coherence AB. And finally, you can find out minus 2 iota delta p minus gamma divided by 4 iota delta p minus gamma 1 iota delta p minus gamma plus omega 1 square and omega p as well. So this is the final equation that I have derived. Now, what the next process is, how we can get the optical susceptibility. So remember, using the polarization, from the polarization P, we know that this is equal to PAB. This is the dipole matrix element and rho AB. This is equation number first. But we can also consider P, the polarization, epsilon naught and chi. Chi is actually the susceptibility. Can compare epsilon naught E and chi, which is equal to PAB rho AB. And from this chi, which is equal to this dipole matrix element rho AB divided by epsilon naught and E. And here in our case, this is EP. I is equal to this. We have calculated rho AB this. So now further, remember this, that omega p, by definition omega p is can be defined rho AB, PAB and EP divided by H cut. So this is by definition we can the the uh, the Rabi frequency we can define like this. Putting the value of rho AB, this one, in this equation. So chi will be equal to PAB divided by epsilon naught and EP and rho AB I have minus 2 iota delta P minus gamma 4 iota delta P minus gamma 1 iota delta P minus gamma plus omega 1 square, and also omega p I can consider this PAP, the dipole matrix element, EP divided by H cut. So let's see, this EP will cancel with this one, and finally we have the susceptibility, which is equal to this and this, a b absolute square divided by epsilon naught H cut and minus 2 iota delta P minus gamma 4 iota delta P minus gamma 1 iota delta P minus gamma plus omega 1 square. This is the optical susceptibility that we have calculated here, but this is only for a single atom. Now in our atomic medium, we have a million of atoms. So this we have to apply it for a number of atoms. So for a many number of atoms, we have n number of atoms, PAB absolute square divided by epsilon naught h cut, and this thing. We have this one. So this is the optical susceptibility. The optical susceptibility is the response of the medium. We are looking for the profit when it is the profit is propagating inside the medium. So what will happen to the profit? Optical susceptibility has two parts. One is the real part and the other one is imaginary part. So optical susceptibility is real of chi plus iota imaginary of chi. So this part gives us the dispersion and this part gives us absorption gain as well. So why this is dispersion, why this is absorption? So this actually is related to the phase and this actually is related to the amplitude of the profit. This is the optical susceptibility of the atomic medium that we have already derived, and now we are looking for the imaginary part of the optical susceptibility when omega 1 is equal to 0, means that there is no strong field applied for that medium. So what will happen? Let's see. Here we want to plot the optical susceptibility, then we get an absorption peak just like we have already discussed in the previous lecture. Now what will happen if we switch on the control field? Let's see the result. Yes, we get a transparency window with two absorption peaks side by side. So actually this is the transparency window, and this has been achieved when an electromagnetic field, a strong electromagnetic field is applied and a probe field is propagating through that medium. Then the probe field can be transmitted at resonance frequency. So this is known as electromagnetically induced transparency. Thank you.